Okay, in this video I'm going to walk through a handful of the examples that we found in our exam number 4 preview. I don't think I'll walk through the entire preview, but most likely just the odd numbered problems. So here we go with number 1. We need to verify this identity, and one of the big tricks that we had mentioned in class is to rewrite our trigonometric components in terms of sine and cosine. And I think that'll be helpful here. So for example, we've got cosine of x on the left side and cosecant of x. It might be worth noting, while we've got cosine of x here, that cosecant of x is really just 1 divided by sine of x. And then I can combine these two, and I can write cosine x divided by sine x, because the product of essentially this fraction and this fraction equals just the single fraction, cosine x over sine x. And then I'll notice by one of our definitions, or reciprocal identities, whichever you prefer to call it, cosine x divided by sine x is really the same as cotangent of x. Now I've done all of this work by working down the left-hand side of the expression. I haven't done anything on the right side, which is pretty good. In this case, we really have two options. I'm just going to continue working down the left-hand side because you might recognize that cotangent is the reciprocal of tangent. And now what we've done is we've shown, just by working down the left-hand side, that the expression is indeed equivalent to what was given to us on the right. So at this point I would say that this identity has been established because, again, we started with something over here on the left and we ended up making it look like what we were given over here on the right. Now, in my opinion, there wouldn't be anything wrong with trying to simplify both sides of the equation. It just gives you something more to work with. Perhaps right at the beginning you recognize that 1 over tangent was really equal to cotangent x. And if you notice that right at the beginning, well, we could have actually stopped here and shown that cotangent of x was equal to cotangent of x. And I would be okay with that as well. Let's try another. Well, this one I think I would attack the same way as I did before and rewrite in terms of sine and cosine. So I'm actually going to avoid that for right now. Let's try number 4. Now right off the bat, when we see this cotangent squared, okay, so hopefully you recognize with this cotangent squared that this is part of our Pythagorean identity group. And then you may also notice that cosecant can be rewritten in terms of sine or cosine, in this case sine. So rather than try to tackle all of this at once, let's do a couple pieces at a time. So the first thing that I'm going to do is I'm just going to rewrite this denominator. And according to our identity list, we know that 1 plus cotangent squared is really just the same as cosecant squared. Now, we could go ahead and rewrite both of these in terms of sine and cosine, or I should say in terms of sine. But honestly, I think that, gives us too much to worry about at this point. Now we've got a division of fractions here, this complex or complicated fraction that we don't necessarily have to deal with. Perhaps more helpful is to recognize that this cosecant, which is a single copy in the numerator, can factor one of the copies of cosecant in the denominator, since this is cosecant of x times itself. So instead I'll write this as 1 over cosecant of x. And again, I'm not doing any work down the right-hand side. I'm just copying down the expression each time. And this is actually a true statement. We should recognize that the reciprocal of cosecant is indeed sine, and sine of x is equal to sine of x. And so I would say that we have now established that identity. And if we were going to try number 5, I think it looks kind of intimidating at first, but we can again use a lot of the same techniques. And one thing that I might try different here is I might multiply this secant of x to the left-hand side of the equation. If I multiply both sides by secant of x, that'll effectively move it to the left-hand side. And so what we'll have then is the phrase secant of x times cosecant squared of x times cotangent of x times sine of x, and all of that is supposed to equal 1 plus cotangent squared of x. And so right off the bat, I'm now working on both sides of the equation, which is fine. Sometimes we do just work on one side or the other, but I've chosen to work down both of them. Now, what I recognize here is that 1 plus cotangent squared of x can be rewritten as cosecant squared of x. And I'll just copy down the left-hand side. I've done this, and I now notice that if I divide both sides of the equation by cosecant squared of x, I can effectively get them to disappear, because there is a cosecant squared of x that exists on both sides. And now we've got a slightly simpler expression on the left that's supposedly equal to 1. Well, if I choose to rewrite this in terms of sine and cosine now, I end up with 1 over cosecant x, 1 over cosine x times cosine x over sine x multiplied by sine of x, and I'll just pretend that that last sine x is written over top of 1, and perhaps you can see what's about to happen now. As these three fractions multiply together, the numerator cosine x and denominator cosine x will factor to 1. The numerator sine x and denominator sine x will also factor to 1. And we've now shown that 1 is indeed equal to 1 using all the various forms of the trig identities. And this is a true statement. So I can say that we have now established this identity. Now clearly this would be a very unusual expression to find in the middle of a larger problem, but if you did spot this expression, cosecant squared x cotangent x sine x multiplied together, that is now known to be equivalent to 1 plus cotangent squared x over secant x. Perhaps not so useful, but a good exercise in understanding how to establish and work with our trig identities. Okay, so in problems like number 6 here, we're going to use identities to find the value of each expression, and we do have 2 of them in this problem. We need to find cosine theta and cotangent of theta. We're not looking for theta by itself, but cosine of theta and cotangent of theta. And what we're told is that sine of theta ends up equaling 1/5, and cotangent of theta has to be negative. Now that's going to be helpful for us because we have to locate this angle before we can commit to answering cosine or cotangent. We have to know where this angle sits. Now if you remember your phrasing with our unit circle, all students take calculus, this is meant to remind us that all trig functions are positive in the first quadrant. Only sine or cosecant is positive in the second quadrant. Tangent or cotangent is positive in the third quadrant, and then cosine or secant is positive in the fourth quadrant. So if we're told that sine theta is equal to 1/5, now that's a positive number, so the angle that we're dealing with could be sitting here or here, either the first or the second quadrant. All trig functions and sine trig functions are positive in the first or second quadrant. But then we're also told that cotangent has to be negative. Well, cotangent is negative in the fourth and in the second quadrant. So the only position where these two align tells me that the angle has to exist somewhere in quadrant 2. So I'm just going to make a side note here that pi divided by 2 must be less than, well, we'll use not the equal sign, but less than theta, and theta must be less than pi. So we know that this angle has to exist somewhere in between pi over 2 and pi radians. Now that's good to note because when we go to find the answer, cosine theta, if we're talking about a theta value here in the second quadrant, cosine of theta has to be some negative number. When we talk about cotangent theta, again we're in the second quadrant, and we were already told this too, cotangent of theta has to be reported as a negative number as well. So this preliminary investigation helps us to identify the symbol that goes in front of the numerical value. Now from here what I might do is I might just draw a representative triangle here. We don't know what theta is, but we do know that sine of theta is equal to 1/5. So that tells me that the opposite side length in a right triangle is 1, while the hypotenuse is 5. So using the Pythagorean equation, I know that 1 squared plus, we'll call this one b squared is equal to 5 squared. So with 25 minus 1 equal to b squared, then b by itself is either positive or negative square root of 24. Now, since we know that the angle sits in the second quadrant, it would actually be appropriate to say that b is equal to negative square root of 24 and negative square root of 24 only. That would produce an appropriate value that exists over here in quadrant 2. And since we're dealing with angles that exist in quadrant 2, somewhere over here, and we've actually got a completed right triangle at this point, I think it would be appropriate for us to go ahead and answer this question here. Cosine is going to require the adjacent side length to be divided by the hypotenuse. So we know that b is negative square root 24, so we'll report this as negative square root 24 divided by 5. And for cotangent, we want the not opposite divided by adjacent, but instead adjacent divided by opposite. So we want negative square root 24 divided by 1, or quite simply negative square root 24. Now I'm okay with both of these answers, and I think Math Excel would be okay with them too if you saw a question similar to this presented to you on Math Excel. However, it is worth noting that this square root of 24 can be simplified. The square root of 24 can be reduced to the square root of 4 times the square root of 6, so therefore the square root of 24 is really just equal to 2 times the square root of 6. And so that tells me that this solution here could also be written as negative 2 square root 6 divided by 5, and this one could be negative 2 square root 6. But here again, either of those would be acceptable from my perspective. Let's try another one. This time, if we were to start with the right triangle, we know that tangent is equal to 7 over 3, so theta is equal to opposite over adjacent side, so we've got 7 over 3. But we're also told that sine must be positive. Now, this is actually pretty good for us, because when we consider our right triangle here, sine will be positive in either the first or the third quadrant. Sorry, not the third quadrant, the second quadrant. And tangent, which is reporting as a positive number, is either positive in the first or the third quadrant. And again, I'm just telling myself, all students take calculus. That's a quick way to remind you where your trig functions are going to be positive. And the only quadrant that contains both of these is here in the first quadrant, so we know that our angle has to exist somewhere between 0 and pi over 2. So not only is this sketch of our triangle over here appropriate in dimension, it's also appropriate in its position as well. So this angle can't exceed 90 degrees based on the orientation that it's been drawn. And so I think if we continue to solve this triangle from here, our results should be pretty straightforward. Again, we know the Sorry about that interruption. They're testing the new PA system here. So anyway, as I was saying, we actually have a nice representative right triangle for us to work with, and we can utilize our Pythagorean identity. The side length c, in this case, the hypotenuse, squared is equal to 3 squared plus 7 squared. So c by itself is either the positive or negative square root of 9 plus 9 plus 49. And I don't believe that can be reduced. We'll go ahead and leave that as the square root of 58. Now, in most, if not all cases, we consider the hypotenuse to be a positive measurement. So even though algebraically we think the result could be negative square root of 58, let's go ahead and report that as positive square root 58. If there were to be a negative symbol, we would generally account for that either with the horizontal or the vertical side length. In this case, we don't need that because all of our components are positive in the first quadrant, so we're good to go there. When I need to address the result for secant of theta, well, I know that secant of theta is 1 over cosine theta, and we know that cosine is 3 divided by square root of 58. And while this would be an okay answer, I think we can do a little bit better. 1 divided by this fraction, of course, is a reciprocal, and the reciprocal of 3 over radical 58 is radical 58 over 3. And with regards to cosecant, we'll take a bit of a shortcut here. Cosecant is the reciprocal of sine. Sine we know to be 7, the opposite side length, divided by the hypotenuse. So 7 divided by radical 58. So 1 over sine theta. And the reciprocal of 7 over radical 58 is radical 58 over 7. And there we go. So the questions like 6 and 8 look to be a bit confusing at first, but I would argue that if you can pick it apart and read for context clues within the problem, you should be able to establish your results using either right triangle trigonometry or perhaps even trig identities. Now, speaking of trig identities, we do have to find the exact value of cosine of -105, and this is not one of the angles that we had memorized in our unit circle. So as the instructions indicate, we can use a sum or difference identity to help establish this result. And so what I'm going to do is I'm going to make a note here that -105 is equal to either the sum or the difference of two other angles that we should know from the unit circle. And so I'm going to use -135 plus 30 because those are two angles that we should know from the unit circle. And as a reminder, we've got 30 degrees, which is the first angle above horizontal. This one's 30 degrees. -135 means we have to travel clockwise, but that's going to be the 45-degree angle in this quadrant. So 180 degrees would be a half circle, and 45 short of that leaves us right here. So these are two positions that we should know about within the unit circle. That's what I'm going to use to answer this particular problem. If there was another combination of two angles that you recognized, feel free to use them. We should both end up with the exact same result. Since I chose this combination, this is a sum of two angles using the cosine rule. So I need to use the sum identity for cosine. And that's the one that said that cosine of A plus B, or alpha plus beta, is cosine of alpha times cosine of beta minus, this is the opposite symbol of what was given to us here, sine of alpha times sine of beta. And so to be abundantly clear, I'm going to label my points up here because this is where sine and cosine are coming from. My beta value has an x coordinate of radical 3 over 2 and a y coordinate of positive 1/2. For alpha, my x coordinate is negative radical 2 over 2, and my y coordinate is also negative radical 2 over 2. It's important to know these positions so that we can answer these questions or address these components without the use of a calculator. And if I didn't stress this at the beginning well enough, this entire exam should be done without a calculator. I don't know if I mentioned that at the start or not, but the entire thing can and should be completed without a calculator. So back to where we are. Cosine, the x value for alpha we know is negative radical 2 over 2, and cosine of beta, the x value at beta is radical 3 over 2 positive. Sine, the y value at alpha is negative radical 2 over 2, so sine at beta, the y value at beta is positive 1/2. If we simplify, we get negative square root 6 over 4 for this multiplication, and we'll subtract negative radical 2 over 2 times 1/2. That's negative radical 2 over 4. Of course, you can see that the subtraction of a negative is going to turn into a positive, and we have a common denominator here, so we can say that negative radical 6 plus 2, radical 2 divided by 4 is the precise result for cosine of negative 105. If you encounter this question on Math Excel, they'll likely walk you through the solution so that the first term in the numerator is positive. So they'll go with positive radical 2 minus radical 6 divided by 4, and they do mean the same thing. Because addition is commutative, they just switch the order of those two, and both would be just fine. And I would use the same or similar technique to answer number 11. For number 12, well, that's the same rule as before, so I'll ignore that. Hopefully you recognize this as the sum identity for cosine. And so if you recognize that, then of course you can address what this will end up looking like. Let's try number 13. Now with this tangent, I've got the sum of two tangents in the numerator and I've got a subtraction in the denominator. This tells me that we're dealing with the sum identity for tangent as well. If the symbols had been reversed, if this one was a minus while this one was the plus, then I know we'd be dealing with a difference identity for tangent. But this is the sum identity for tangent, so that tells me that if I take these two angles and treat one as alpha and this one as beta, as long as the pattern holds, which it looks like it does, then really this entire expression is really just the same as tangent evaluated at 80 plus 100. Clearly, 80 plus 100 is 180, and so if I'm trying to find the exact value of this original expression, all I need to do is find the tangent result for this particular position. And if I'm thinking y value divided by x for tangent, that would be opposite divided by adjacent if you're thinking of the triangles. But in this case, y divided by x, that would be 0 divided by 1, or in other words, 0. So this entire expression, as perhaps impressive or difficult as it looked, is really just equal to the number 0, and we know that because we followed the procedure for the sum identity for tangent. Number 14 looks like it's using the difference identity for tangent, so we'll go ahead and skip that and jump down to number 15 instead. With number 15, hopefully you recognize that negative 4u and negative 3u are the two angles in question here. So essentially this is alpha and beta, alpha and beta. Whoops. And with the identities, I'm sorry, with the expression sine times cosine, cosine times sine, with a subtraction in between, this tells me that we're dealing with the difference identity for sine. So that again tells me that we'll take sine of alpha, negative 4u, minus beta, which was negative 3u. Now these two have like terms, or are like terms, so negative 4u plus 3u is negative u, sine evaluated at negative u, that is. And since this is a even-odd identity, we know that sine is an odd function, so this result is equal to the opposite of sine of u. So just to double check the instructions on this one, it just says to simplify. There's no way for us to really solve this for you. We don't have an equation or anything to deal with. So I would probably report this as my final answer, although I would say that this is acceptable as well. This final result stemmed from our understanding of even-odd identities, although this problem I think was really just a test of your understanding of your sum and difference identities. And to finish out this practice test, we'll take a look at this particular set of questions. For angles alpha and beta in the figures below, find sine of alpha plus beta. So we've got two different triangles, therefore two different angles are being established in the lower left-hand corner. And our job is to find sine of alpha plus beta. Well, sine of alpha plus beta is really just sine of alpha times cosine beta plus sine of beta times cosine of alpha. This is our sum identity for sine. So if I can identify what sine of alpha and cosine of beta and sine of beta and cosine of alpha are equal to, based on the triangles that are given, then certainly I can establish this result. So let's take a look at the triangles. Again, with the Pythagorean equation, we should be able to identify the missing side length. We know that 1 squared plus 2 squared is equal to c squared. So 1 plus 4 is 5. The square root of 5 is equal to this side length. For beta, same sort of thing. We've got 3 squared minus 2 squared equals this value squared. So therefore, 9 minus 4, which is also 5, that's kind of interesting, tells me that this side length is actually equal to the square root of 5 as well. So if I need to evaluate sine of alpha, I need the opposite divided by the hypotenuse relative to that angle measure alpha. So we now have sine of alpha is equal to 1 over square root of 5. We need cosine of beta. Now, beta is in the second triangle, so I need the adjacent side length divided by hypotenuse. So we want square root 5 divided by 3. Sine of beta, coming back to the second triangle here, sine of beta requires the opposite divided by the hypotenuse, so 2/3. And then cosine of alpha, adjacent divided by hypotenuse, we've got 2 divided by square root 5. Now, these results for sine, cosine, etc., would not have been known. These values here would not have been known unless we had solved the triangle previously. So that's an important step. Even if the triangles aren't provided, it's a good idea to sketch one in order to utilize these identities. And when it comes to multiplying these two together, the square root 5s are going to cancel, and we're left with 1/3. And in this case over here, we have 4 divided by 3 radical 5. And I'm okay with this as a final answer. You could take the time to simplify or find a common denominator. Actually, finding a common denominator wouldn't be too hard to do. If we multiply this fraction by radical 5 over radical 5, now we have a result of radical 5 plus 4 over 3 radical 5. That would be a good answer. And then if you wanted to rationalize the denominator, you could do that as well. That would require multiplying the numerator and denominator, again by radical 5. Now that we have a single fraction, this is going to be relatively easy to do. Upon distribution, we get 25 plus 4 radical 5 divided by 3 times 5, which is 15, and that also would be a fine and acceptable answer. So I hope this walkthrough helps. There are lots of different questions that we could ask in this type of exam, but really our focus is on your ability to use and establish trig identities, and of course being able to do so without a calculator. Calculators really don't help much in here other than to verify your work if you were using the graphing technique that we talked about in class. So having access to one really shouldn't benefit you here whatsoever. So again, this is a test over your understanding for identities. When we get into our next unit and we solve equations, well, then a calculator might be more helpful. If you've got questions, please let me know. You can reach out to me through Schoology or by email, and I'll do my best to answer them. Thanks for watching.